I'm gonna unmute them. Morning, girls.
Good morning.
Goes it? It goes well? Yeah.
My dad burnt his first batch of sap.
Oh no, I was waiting to see the final product.
It was like 20 gallons of sap.
No way. 20 gallons?
Is that a drop?
No, but well, explain what you're talking about. They don't know what you mean.
So my dad's tapping my trees, which means he's taking the sap from the trees and is gonna make maple syrup and maple products.
Where do you live?
And so he was boiling down the sap that we got with the first batch, and he was gonna make maple syrup. But then, since he was on a call, he forgot to check on the sap, and it burnt because it cooked too long.
She's in Connecticut, so.
Yeah, I know sap is gonna remove them for you.
But I wasn't half disappointed. It smelled like maple syrup. I'm like, oh, it smells like heaven.
Is all you have to do cook it down? Is that the only thing you have to do to it to make it?
Well, he also
Already sweet, I believe.
he takes like a strainer you use to strain out the water from noodles to get like other junk out of it.
Yeah.
And stuff, but really all he does is boil it down and stirs it.
That's pretty cool. Does he have like a giant vat? Because 20 gallons is a lot.
I don't know.
What's he cooking it in?
I don't know.
Yeah, something big, I imagine.
Like a big metal pot that boils things down. I don't know what it's called.
Because I don't actually like the fake maple syrup. It's just made out of stuff. I just have that because it's actually sweetened already when it's come out of the trees, and then we just have it plain in the system.
Yeah. Usually, I think you cook it down because it caramelizes whatever sugar is in it, and obviously condenses it.
I like the real maple syrup.
Yeah, real maple syrup is much better.
But yeah.
So
yesterday my mom saw a lot of smoke coming off of it, and so she checked on it and it was burnt.
Oh, that stinks. Oh man. Is there still more left to do, or is that his only shot?
No. A lot of our trees are big around, so we'll get a lot of sap, and we're still getting sap.
How many
acres?
We're gonna
try again this week because this week was supposed to be much warmer.
How many trees do you have to tap to get 20 gallons of sap?
We're right now tapping 3, 4, 5 trees.
That's it? Oh wow.
One of the trees has 2.
Oh wow. I figured you'd have to tap more trees than that. That's pretty impressive. Well, okay. Let's go ahead and
our trees are really fat.
Yeah, that's really cool though. Like, I had no idea that you could get that much sap from only that many trees. I thought you'd need more than that.
Well, we haven't tapped them at all. This was the first time my dad was starting to tap our trees.
Is this the first time he's ever done it at all, ever? Or has he made syrup before?
Pretty sure this is the first time he ever has done it because cool. I don't know.
Very cool. Excellent. Well, I'm gonna hand here we go. I'm gonna hand some stuff back to people real quick, and then Jocelyn, your package has been shipped. If you don't have it today or tomorrow, I'd be surprised. And Senya, you guys are gonna come pick up yours today, your mama said. So Ella, Lily, Alec, you. You had it, sweets. There you go. And Ella again. All right. So we made a change to today's lab because one of the chemicals I thought I had, it turns out I don't have. I don't know what happened there. I don't know if it just didn't show up on the inventory. And I tried to check off my inventory as it arrived, but I think I missed something. So anywho, I've adapted it. It's pretty similar to what we were going to do anyway. And then for you girls that aren't here, all you're going to need to do is just watch and comment on the video. We're going to put the video together here today. We're going to combine everybody's data again and put it together. And basically it's a reaction time lab, and it's called an iodine clock. And that's what the other one was too. It was also an iodine clock. So we'll get it all together and get some footage, and hopefully I'll have it out. If not today, tomorrow. And it's just easy. It shouldn't be very long. So just watch and check. All right.
Okay.
And you all, before you leave here today, get your Q4 stuff off the dining room table. Everybody's packet is there and labeled. Yours is in the mail with all the rest of your lab stuff, and Senya, yours is here on the porch waiting for you. So everybody's Q4 stuff is done. So all of your lessons from here to the end of the year are ready to go. I can't tell you how excited I was about that. All right, let me get you guys started. Here we go. So everybody had a nice weekend? Yes? No? Maybe? Kind of? Sort of? Why is this not get out of here?
I'm jealous. My grandma got to go to Cracker Barrel for breakfast on Sunday.
Oh, I love Cracker Barrel. Who likes Cracker Barrel for breakfast?
I do. There was a Cracker Barrel, there was a Cracker Barrel near our house, so we would sometimes go for like dinner or something. Oh, let's get pancakes.
There you go.
I love the pancakes.
I like the pancakes too. I like breakfast. I like to go out for breakfast. I like people to serve breakfast for me. Like I like a big breakfast meal, but I don't like to cook first thing in the morning. I'll do it if there's company here, but you know, for just me, I don't want to do it. So my birthday was Saturday and Drew actually cooked me a full breakfast. He made pancakes, bacon, eggs. It was amazing. So props to Drew. It was a great Christmas present. I was so happy. You're not trusted around the stove, Eleanor? No?
I am. Yes. Yes.
Knives are good, but not the stove?
Yeah.
Okay. All right then.
Me and my sister are allowed to be by the stove.
So Senya, you're at an appointment, aren't you? Yeah. Okay. So Senya's at an appointment. So she's watching from some office. Look at that. That's so funny. Yep.
I baked this 3-layer cake when my mom was in Tennessee. We had a camper.
Oh,
And I was like, ooh, I want cake.
there you go. All right. So today we're going to talk about reaction rates. So reaction rates, and where our lab's going to be a reaction rate lab, but it's like I said, it's going to be altered. It's going to be a little different than the one you initially had. So the one that's in there, you can just put a little X on top or whatever and leave it. We're just going to finish it in class today, and it's going to be a complete or incomplete. And I saw when I checked yesterday was the last time I looked to see how you guys were doing with getting your unit test complete. And some of you had gotten to it and some of you hadn't. So don't forget to get to that.
I think I aced it.
I know. Your mom talked to me. You had,
Did you read manual grades?
I did yours. Mhm. All right. So what is required for a chemical reaction? So we're going to talk today about something called collision theory. We're going to talk a lot about collision theory. A lot of what we call chemical kinetics, which is the science of chemical reactions, revolves around collision theory, which actually I think would be a great band name. If anybody ever starts a band, I'm encouraging you to use the name collision theory. I think that's a great name for a band. So what's collision theory? All right, so there are three main components to collision theory. It's that particles must collide, obviously, that they have to have sufficient energy when they do collide, and they have to have the correct orientation. So just for a real quick example before we get in depth, if you had two Legos, all right, and you had Legos that were gonna stick together, actually, give me 2 seconds, I'm gonna grab two Legos because they're all right here. They're all right here.
It's actually pretty easy to demonstrate.
All right, so I have two Legos here, and these are going to be my two particles, okay? And first part of collision theory is that they must collide to stick together. If these guys pass each other in space and they never run into each other, they're obviously not going to combine, and you're not going to get your chemical reaction, which will be when your new thing is created, right? I have two separate things, and when they join together, there'll be a new thing, all right? We can pretend that they'll be totally new. They have to have sufficient energy. So if I just kind of like,
Drop it.
like nothing's gonna happen, right? Even if I set it directly on top, that's not working, right? I have to have enough energy to lock it in place. And then the last thing is orientation.
You can't attach it to the wrong.
I can't do this, can I? This doesn't work. And I can't do this. This orientation isn't correct. In order for it to work, I have to have correct orientation. The key and the lock have to go together in order for them to fit, right? So that's the idea of collision theory. So here's a quick little collision theory video, which kind of covers that, but has some good animation. If it would go, here it goes. Hopefully we won't have a commercial. I bet we will. It's going to tell us to VRBO or something. Yeah, I love these animations. I want to be able to do these. These look fun.
Here's a beaker of cold water and a beaker of hot water. When you add sugar cubes to them, the one in the hot water will dissolve faster than the one in the cold water. To explain the different rates of reaction, Max Strauss and William Lewis came up with collision theory in the early 1900s. The first assumption of collision theory is that the particles must collide with one another in order to react. Most particles will act like billiard balls in a game of pool, and when they collide, they bounce off each other. The collision itself isn't all that's for a reaction to occur. The particles also need to have enough energy, enough speed to break and form new bonds when they collide. The minimum energy required for a reaction to occur is called the activation energy. Some reactions require very little, and some need a lot more to get started. Generally speaking, most reactions will occur faster when the temperature is increased, because temperature is the average kinetic energy of the particles. With more kinetic energy, they will be more likely to have enough activation energy for the reaction to occur. But for some reactions, there is still one more factor, orientation. Even if the particles collide with sufficient speed, if they aren't at the correct angle, a reaction won't happen. In this example of nitrogen monoxide and ozone, the reaction didn't occur because the oxygen of each molecule touched during the collision. In this the same two molecules, the nitrogen touches an oxygen and the reaction occurs, making oxygen and nitrogen dioxide. The orient was correct, so the reaction could occur. So in summary, the three key ideas of collision theory are that particles must collide to react, they must have sufficient energy to break and make new bonds, and they must collide with the correct orientation. Thanks for watching this episode.
We have a rat too.
Don't forget to like and subscribe and follow me on Twitter at ScienceTech.
She has her own little rat. How cute is that? I like that little rat.
Copied off her.
I know. Well, you know what's funny? I found Rico on a just on a search, on a random Google search, and it was from like DeviantArt, one of those pages like that where people add their own art and display it. And I've contacted the guy who drew Rico more than once and said, I'd like to buy the rights to this, please, because I'm using it already. Can I please pay for it and buy the rights to it? And the dude never writes back. I don't know if he speaks English or so.
Email him a lot.
Yeah, there you go. So particles must collide. So here's what makes particles more likely to collide. Oh, Gunter has been sipping the cuckoo sauce again, and he's about 15 minutes off, and I've got to adjust him. So don't listen to him today. I finally made him wake up, and he's still, I swear, he goes into that little wooden door, and the door shuts, and I don't know what he does in there, but he parties so hard that he doesn't know what time it is and comes out at the wrong time. So that's right. Yeah, So particles must collide. Particles are more likely to collide if they are present in increased concentration. This makes sense, right? If you have a super concentrated solution full of particles that are needed to react in another solution, and there are more of them in here, your chances of them bumping into each other are higher than it would be if there were very few. It's just like kind of like playing the lottery or a raffle. The more tickets you buy, the more likely you are to win, right?
Yeah, it's still.
Even though it's really small. I mean, if 5 million people buy tickets, you're probably not going to win. But if there are only 10 people buying tickets and you bought 5 of them.
I the lottery to succeed if you're going to like a Georgia thing, because
Yeah.
That's how you get a scholarship.
Right. So when it comes to stuff like that, you want to increase your chances of winning, right? So you the more you do, the better. Kind of like we were talking about this with Cole this week because he did an online test at one of his dual enrollment classes, and there were a couple of multiple choice questions that he didn't get to. So we were saying to him, okay, so here's a really good strategy. As long as the test will let you go back before you do a final submit, then when you're going through, just answer all the multiple choice. Even if you don't think your answer's right, if you don't know, put in, the one you think is best, write down that number for that question, keep going. And then if you have time, then go back, but always answer all of them because it increases your chances of winning. It increases your chances of a hit. If you don't answer it at all, you got no chance, right? Same thing with this, the increased concentration. So then also, if they have higher kinetic energy. So what increases the kinetic energy? So what is the measure of the average kinetic energy of particles in a substance? What's the word for that? It's the definition of a word. The average kinetic energy of the particles in a substance. What do we call that? You guys know it. Sure, you know it. What is the measure of the average kinetic energy of the particles in a substance? Temperature. Temperature, right? Temperature is your average kinetic energy. So if you have higher kinetic energy, you're going to have a better chance that your particles are going to collide. So this is why, like in the video, if you have a cube of sugar in cold water and a cube of sugar in hot water, it's more likely to dissolve in the hot water. And that's because the water has more energy. So the particles are all banging around. That makes them more likely to collide, and it gives them the second part of collision theory, which is about having the right energy when they do collide. Because if you think about it, if Eleanor's just sitting on the couch and she's not moving, and I'm sitting over here and I'm not moving, we are not very likely to run into each other. If we both stand up and sway around, we're still not likely. But if Eleanor increases her energy to the point where she's bouncing off the walls, she's a little more likely to run into me, right? So that's going to increase her chance of colliding. Yeah, it's going to increase her chance of colliding with me, which is what we need for the first part of collision theory. But it's also going to give her the energy so that when she does, it's not just like bumping or brushing me. She actually smashes into me, which is what you would need, right? For these particles to interact with each other. And then if they have a greater surface area, that makes them more likely to collide. All right, so if you have a particle, let's say you have a molecule. And let's say this is your molecule, okay? And the part of your molecule that needs to collide with the other substance in your solution, let's say, in order to react, is this part. It's going to be harder because it's this tiny part. But if the part that needs to collide for the reaction is the bigger part, then you're going to have a better chance of it actually colliding correctly. So that has something to do with the shape of the molecule or the compound. And it also has something to do with how much of that compound is exposed. So go back to your sugar cube. We talked about dissolving, right? We talked about how likely it is for something to dissolve. And we said that surface area mattered. Remember the sugar cube versus the granulated sugar? Okay, so who has ever used a bath bomb? I like bath bombs. They're a ton of fun. All right, so when you put the bath bomb in the bath, what happens? It does what?
It dissolves
Yeah, it fizzes too. Why is it fizzing? Do you know why?
because of the chemicals.
Yeah, do you know what they are usually?
I've made bath bombs before.
You have? Oh wait, Jocelyn's made them. Okay, what'd you put in them? Do you remember? Can I guess?
It's made of everyday ingredients that you make.
Did you have baking soda in it?
I don't remember. It was like what I was.
Probably. Have you made them before?
Yeah.
Okay,
so
what
you put
went in
baking
them?
soda, and if you want them to have a scent, then you have to buy a little scent thing.
Mhm.
It's like baking soda and I think some vinegar, but you don't want to put too much vinegar at once, otherwise they'll have too much of a chemical reaction.
So sometimes people put, yeah, or you can put vitamin C. Anybody ever put vitamin C in them? You've done that? Okay, so what's vitamin C? Does anybody know what it is? Like chemically, what is it? What its chemical name is? It's ascorbic acid, and it's actually what we're using in lab today. So vitamin C is an acid. So, and baking soda is what? Sodium bicarbonate. So it's what? It's a base. So if you have this dry acid and this dry base, all right, and you mash them together, yeah, they don't do much. But when you put them in the water and they start to dissolve, more of the areas of each of those compounds come in contact with the water, right? So that's a surface area thing for dissolving. But it also allows them to, so in the water, you have some citric acid that's just dissolved, and it can now get to all of the sodium bicarbonate compounds that are on the outside of that bath bomb. So there's your surface area. It can't get to the stuff inside yet, right? But it can get to the stuff outside. Now, if you took the two compounds, if you took your citric acid as a powder and your baking soda as a powder, and you just, I'm not citric acid, sorry, ascorbic acid, and you just threw it in the bathtub, it would go, and it would be done really fast. You wouldn't get the nice slope. That's true. Yeah. That's why there,
Kind of formula.
you want it to last longer. So you put it in the big bath bomb and it takes time to get all the way through it.
Is there a formula like what surface area times wall equals?
There are some. Yeah, there actually are. There's a lot of them that get really complicated when you get into like higher level chemistry. All right. And then if they're under pressure, and this applies for gases only. So if you put a gas under pressure and say it's a solution of gases and you crank down the pressure on it, you're going to be more likely for the particles of those gases, obviously, to bump into each other because you've just decreased the volume when you increase the pressure, right? You've squashed the size of the container that they're in. And then another part of collision theory, we were saying, particle collisions, I should say, affect the rate of a reaction. So what's rate? Does anybody know what rate means?
Oh no, it's a measure of something.
It is. Mm-hmm.
It's a measure of how much speed. How much?
Kind of like speed.
Fast, how much or something.
Right, right. So how do we measure speed? Let me ask you this. In the car, how do you measure speed? What do you say, Drew? What is it?
Distance over time.
Distance over time. Yeah, miles per hour or kilometers per hour if you're Canadian or whatever. Yeah, so it's distance over time, especially when we're talking about physics. But in chemistry, when we're talking about rate, it is definitely about time, but it's more about the process over time. So particles that are more likely to have sufficient energy. All right, so first we talked about being able to collide. So how do we make it so that they have the right amount of energy so that when they collide, they stick instead of just bouncing off each other? So if they have higher kinetic energy, again, that's temperature. We talked about that. If Eleanor and I are bouncing around the room, you have to bounce at the right speed, just brush by somebody doesn't help. And then, so sufficient energy is required to start a reaction. And what was that kind of energy called? To start the reaction? Activation energy. And it causes the particles to combine. And when particles combine, we call it a chemical change. And then the energy level affects the reaction's rate. So here we are with the word rate again. So particles must collide with correct orientation. All right, this is the third part of collision theory. Correct orientation. Particles are more likely to combine with another correctly oriented particle if what? Let's see. If they're present in higher concentration, all right, that makes sense. If you got more of them, your chances are better. Again, you always want to increase your chances, right? And then how about this? A good analogy for this would be, let's say you had to open a door and you had 5 keys and only one of them is going to fit the door. And then you also had another opportunity with 50 keys and only one of them is going to fit, well, your chances of one fitting the door. You would have a better, I didn't phrase that correctly, but if I didn't know that one of my keys was going to unlock the door, I would rather you give me as many keys as possible, right? And I'm going to try until one works.
Are you talking about theoretical probability and experimental probability?
Yeah, kind of. Because this is theoretical because it's theory, it's collision theory, but it can be experimentally explained, right? Like most.
They're not different. It's kind of similar, but like
Yeah. Yeah. You definitely want a higher concentration if possible, right? Because that makes it more likely that your particles are going to run into each other with the correct orientation. And then if they contact other particles more often, you're more likely for one of those collisions to be correctly oriented. So it kind of just makes sense. A lot of them go together. So temperature, for example, here you go again. You're more likely, if the temperature is increased, they're more likely to have the right energy when they collide. They're more likely to collide to begin with. And they're more likely to collide with the correct orientation because they're likely to collide more times. Does that make sense? Okay, so basically some of these things that can increase your reaction rate apply to all 3 areas of collision theory. The fact that they can collide, the fact that they need to collide with the correct orientation, and the fact that they need to collide with the correct amount of energy, right? So then, what affects the rate of a reaction? So here we are with some other examples of it. So we have chemical kinetics. That's what we call this whole branch of chemistry, where we talk about reaction rates. It's a whole branch. You could probably get your PhD in chemical kinetics. It's that kind of thing. Can you imagine chemical kinetic. The things you can be specialized in science are so vast. Like it was interesting to me because like when I was in
Can I have a PhD in human psychology? Can I get a PhD in procrastinating?
probably.
In like the.
Have you heard the TED talk on that? It's great.
I should probably.
There's a great TED talk on procrastination. You should look it up.
Probably literally get a PhD in human psychology. You could like mainly focusing on.
So when I was in college, we had just gotten 2 new professors to that year, that started that year in the biology department. So the one that had stayed, we had 3 main professors and 2 new ones. And the main professor who had stayed was my advisor. She was amazing. But her specialties in biology, had a PhD in biology, but her specialized areas were neuroscience and like she did a lot with entomology too, which is bugs and things like that. But she kind of focused there. One of the other ones focused a lot on microbiology and cellular development. And the other one did a lot with ecology. So they were missing a big branch of biology, which is someone to work in botany, which is plants. So they were interviewing these biologists, these, fresh out of PhD or in the middle of their PhD program to come teach for a semester, that kind of a thing. So this dude, I'll never forget, because it was my sophomore year, and they asked students that were biology majors to meet these people and take them around campus and, bring them over to the building, escort them, show them around. I mean, it's a women's college, so you get a random dude on campus, kind of helps to have somebody be like, oh yeah, he belongs. So I went and got this guy from the little guest house where he was staying, and I walked him to the science building, and he was telling me about his specialty. So yes, you can have a specialty like chemical kinetics, but this guy's specialty, his focus was paleobotany. So not just botany about plants, but prehistoric plants that are no longer alive. And his thesis and his major research had been done on this particular type of fern. And he started talking about this long deceased prehistoric fern and talked to me for like 15, 20 minutes straight. He was so passionate about this dinosaur fern. And it was amazing how, completely granular he got, nitty gritty about this fern. So we have our chemical kinetics, which is the study of reaction rates. You could spend your life on it. So here's rate. So instead of distance over time, as Drew suggested, which is usually how we go ahead and describe it when we're talking about physics, for chemistry, it goes more along the lines of change over time. So what kind of change? Chemical change in this case that we're looking at. Change over time. So here's a little graphic for you. So it says number of molecules, and you have a substance A and a substance B, I guess, a purple substance and a green substance. And you start up here in this example with more of your purple substance. And over time, it's going to change to your green substance. But if you look right about here is when you have about equal amounts of the both of them, right? So you have equal amounts of purple and green substance, and then it continues to change. There are things you can do to take this point right here and shift it. You can make that change happen sooner or later. And you do that by controlling the factors that affect your reaction rate. So speed at which chemical reaction takes place. And here are the things again. We talked about concentrations and surface area and temperature and pressure with gases. And then another thing is catalysts. So catalysts are something you add, that is the leakiest, something you add in a chemical reaction that increases the speed of the reaction, but it doesn't join the reaction. It doesn't become part of the chemical compounds that are involved in reacting, but it speeds the reaction. And in biology, we have these, right? And they're enzymes, that's what we call them in biology. So the change in the amount of reactant or product per unit of time would be a way to measure it. So you're talking about, are there formulas? So here's one formula, and it's the rate of reaction. It's the amount of reactant used over time, or the amount of product formed over time. And again, here's that point. You can shift that point right or left. So then we have this little guy, inversely proportional. So your reaction rate is inversely proportional to the time taken. What's this mean? So the change in the amount of reactant or product over time taken, they're inversely proportional. Why? Because one of them is the change. If you look back here, let me look back one more, show you. We had right here, you had the amount of reactant used divided by time, and the amount of product formed divided by time. Those things are inversely proportional because as your reactant is used, your product is formed. So as one goes up, the other goes down. Remember what inversely proportional means? One goes up, the other goes down. So as you use up more reactant, you're producing more product, right? So these are inversely proportional. This one goes up while that one goes down. So then if we look back at this little symbol, this symbol is this strange little symbol that doesn't really have much of I tried to find a name for it because I've seen it a million times and I figured it had a name. It doesn't really have a name. It is the symbol for is inversely proportional to. Do you remember we talked about pH and the what did it mean? And the P actually doesn't mean anything except the amount of hydrogen, but it had some big definition for what you could substitute for P. So you have your rate of reaction. Your rate of reaction is inversely proportional to 1 over time taken, or basically your rate of reaction divided by time taken. So here is a great chart. So let's look at these. How do we make our reactions happen faster? So here's our collision theory again, correct orientation. You would have a reaction, your wrong orientation, you wouldn't have any or insufficient. So we're gonna look at them each one by one real quick. So here's your increased concentration. If you increase your concentration, your frequency of collisions goes up and your percent of successful collisions is going to increase. So increasing your concentration of reactants in a solution increases the rate of the reaction as there are greater numbers of particles available to react. This increases frequency of collisions. Makes sense. So how about the temperature? We talked about temperature. Frequency of collisions goes up and the frequency of successful collisions goes up. Your percentage goes up. So your increasing temperature increases kinetic energy. This increases frequency of particle collisions, and a greater proportion of those collisions will have enough activation energy to react. So what about this one? Here's your surface area again, right? Your frequency of collisions increases and your percent of successful collisions increases because increasing the surface area of a solid increases the number of particles that are exposed and available to react. As a consequence, this increases the frequency of particle collisions, increasing that rate again. So here's your pressure one, and this only applies to what state of matter? Pressure applies to gas only, right? And here's your graphic. You know, you're going to squash it down, decrease your volume. It's going to increase your frequency of collisions and your percentage of successful collisions because, once again, they're closer together now. You've made them closer together, they're more likely to collide. So here's catalyst. This is the new one. So a catalyst provides an alternative route for the reaction with a lower activation energy. So this means that particle collisions need less energy in order for reaction to occur and increasing the rate of reaction. So this here, we looked at those graphs before, and here's another one where you have this big hill of energy, and that's your activation energy. You have to have that much energy for the reaction to take place, period. Has to happen. But when you put in the catalyst, what it does is it lowers the activation energy. That's how a catalyst speeds the rate of reaction.
More catalysts.
Well, there's a point where you've got enough, it's not going to do any more than it's already doing. But yes, there's a right amount. There's a sweet spot.
Seems like it would help with rocky people or something.
Yeah, there are catalysts everywhere around you all the time doing all sorts of things. Your body is full of them. But so the catalyst isn't involved, as I said, it's not involved with reaction. It's not a reactant or a product, but it does lower the activation energy. And that's probably something you could also spend your life studying as to why that works. So we also have what we call reaction pathway. And I just don't want you guys to have to worry about this too much, but I wanted you to see it. And it's the minimum activation energy is the minimum kinetic energy that particles must have for a chemical reaction to occur. And this pathway basically is like you can see it as a graph, but it shows all your various stages, and you can expect and anticipate that the same reaction between the same reactants will occur the same way under the same conditions every time. And see, here's an example of it. Here's your activation energy. You need this much for the reverse. You have forward and reverse. So some of these are reversible reactions. So catalyst increases the reaction rate, doesn't change during the reaction. This is a great example of your catalyst. So here's your man trying to push this big old rock over this hill. And here he's got his reactants. Here he's got his products, but it was a little easier for him to just kind of roll it in this example. I don't know why the tool wasn't easier. You would think it would be, but it's an odd choice of a graphic, but you get the idea. Now he's rolling that down the hill. This activation energy is lower. I guess what they're trying to show us here is that the ground is flat. Maybe the catalyst flattened the ground and he didn't need to go up a hill. So they lower your activation energy barrier. Oops, sorry, that's just another graph. Shows the same thing. Here's your catalyst down here. So catalysts, so enzymes are catalysts formed in nature. So when we have catalysts that are part of a natural, organic, or biological reaction, we call them enzymes. And enzymes are actually large proteins, and they catalyze metabolic processes. Now, this will be for next year. We'll get talking a lot about this, but metabolic processes are those that go on inside your body. Yeah, your metabolism is kind of like the rate at which your body runs. So here are some examples. This is cool. I got you pictures. These are great graphics. So here are some examples of catalysts that exist in your body. Do you recognize the names of any of them? Do any of them look like something you've maybe heard of or? Yeah? What do you think? How about the one in the middle at the top? Do you know what that one is? Hemoglobin. Anybody ever heard about hemoglobin? What it does? You ever go to the doctor and they do the thing where they prick your finger and they use that little capillary tube, take a tiny bit of blood,
I hate it.
and then they go put it in a centrifuge and they spin it around? So part of that is they're checking your red blood cell count, and that has to do with hemoglobin. And here's why. So this is how enzymes work. We have these things called substrates, and this is what they react with. And basically it's a lock and key. There's a lot of lock and key. Like we just talked about how substances and particles have to have the right orientation, and that's a lock and key. When we get into biology, we'll talk a lot about antibodies having lock and key. Like that's how vaccines work, guys. Like last Friday, I went and got stabbed for coronavirus, right? So it's making my body produce antibodies that will look like basically like a key that fits only the coronavirus lock. So-
You're basically kind of telling your body, oh, you don't know what COVID is. This is COVID. If you see
This is what it looks like.
white
Yeah.
blood cells go-
It's like a wanted poster. So say you've never seen that. Have y'all seen the wanted posters on the billboards around here, on the light up ones? So for those of you that don't live in Forsyth County, there is currently an FBI most wanted fugitive that they saw last in Georgia, because they keep putting his face up on these, like the video billboards around here, the light up ones. You've seen it? So I've never seen him in my life before. I've never encountered him, but I know what he looks like now. So should I run into him, I'll go, oh, I need to be careful about that guy and I need to call the cops, because
What does he look like?
he's an Asian guy and he looks to be about 30 something. He was at
What do you do?
Okay.
he was at MIT, and then he was,
So what's the
There
difference?
there were like five or six cops in our neighborhood.
oh yeah,
There's this Indian guy
uh-huh.
who lives like one house away, and there were like 2 ambulances and like 6 cops.
That's always disconcerting, right? What's going on?
At the front of his house, and then 2 cops
It's
at the
probably,
back.
Mm.
probably you haven't getting arrested. I'm guessing it's just something happened to them.
Could be.
A lot of times actually come to acts.
Yeah, they will sometimes if they have nothing better to do. They get bored. Yeah. Well, this guy apparently is wanted for murder. But anyway, his face is everywhere. But my point is, you've seen him, and that's how antibodies work. Antibodies are like, it's like showing your body, your immune system, a picture and going, when you see this, react. So hang on real quick. Let's wrap up this because we got lab shortly.
Real life, it's like the easiest
So
thing.
here are your substrates. Here's your enzyme. It's a lock and key. That's just how antibodies work too. Same thing. So here are some enzymes and what they react with or join with. So this one right here, sucrase. You have an enzyme called sucrase, and it works with
Sounds like
sucrose,
that's sugar.
and that is a sugar. And it's found in your small intestine, but without it, man, you would be really in a bad way, because you'd have so much sugar in your body that it could actually, you can go into coma if you get too much or too little. So we measure reaction rates in different ways. We can measure reaction rates. Gas, we can measure with a syringe, actually. They do this sort of thing here where the gas will push the plunger out. We can measure them with mass. We can measure it with color, pH, or electrical conductivity. Today is going to be color. So concentration is something we measure really often. So here's your, how can we measure the rate of reaction? Measure the concentration of A as it decreases, or measure the concentration of B as it increases, because as we said, products and reactants are inversely proportional when it comes to what changes during a reaction. So reaction rates can be represented graphically. That's pretty obvious. You have an original reaction, a faster reaction, a much faster, and a faster, even more faster. And then rate laws. You guys aren't going to be doing rate laws, the other group will, but I want you to see them. So it's the rate determining step that controls the reaction rate. The rate determining step is going to be basically something along the way that controls the speed of the entire reaction. So it's the slowest step. So if you look here, this is a great graphic example. You see this opening here is kind of big. This one here is kind of big, and that is tiny. See that tiny one there? You see that one, Jules? This tiny one here? So this small one right here, this is going to determine how fast that sand flows. It doesn't matter how big these other ones are because it has to get through the little one first. And if you flipped it over, the same would be true. The sand would pile up, you know, in this part, but it's not going to all fill that bottom bulb until it gets through the slowest step. So it's your slowest step that is your rate determining step. And then you have these other things called intermediates, and that would be these other pieces along the middle. And here, look at this. This is what these dudes that do chemical kinetics for a lifetime, this is what they do all day. That's a lot of like mathy. They love that stuff. So your homework, research enzymes in the human body. Let's take, yeah, I would love, no, real quick. Do y'all still have them with you? I think you should, right?
Yeah.
Because weren't these keep in your binder? We've got about, ooh, we're almost late, but I would love it if you guys could really quick share. If anybody wants to share real fast, and then we really have to get over to lab. But
No, I have a full page full of it.
you have a whole page full of it? What have you got? What enzyme did you find?
We did. If I can find it, my handwriting is really crap.
Did you pick one, Drew? Do you have one, Alec? Eleanor?
I didn't pick an enzyme because it just said research about enzymes and what they
Then it
are.
said write a little bit about something you learned.
Yeah, I wrote what enzymes are and how they work.
Oh, okay.
Write a little bit
About any type of enzyme and how it works. What do you have, Alec?
Oh, that enzymes are body when it works. That's the red end. No, I didn't remember.
Okay. Do you have a specific one?
The one I picked was in the small intestine.
First of all, do we keep this in our binder?
Yeah, you can keep it in your binder.
I did the small intestine.
You did the small intestine?
I just.
Okay.
It says there's also one in your pelvis or something.
Pancreas, probably.
That's what-
Pancreas, yep.
I just did how many there are in the human
How
body.
many did you find?
Enzymes are
Proteins, yep.
protein chemicals and a reaction that occurs in our body. There are approximately 1,300 different enzymes.
1,300. Thank you, Eleanor. That's awesome. That's awesome. All right, so
I interpreted your question as.
it's okay.
What about any type of enzyme? How about you, like, write
It's all right.
true about all types of things?
No, it's okay. But we do have to go ahead and get to lab. So we'll say goodbye to Jocelyn and Sonia.
Goodbye.
Catch you later. No, we're doing something different today, remember? So you don't have it. You don't have to worry about it. Bye, guys. See you later.
Bye.
Yeah, just bring your pencil and a blank piece of paper if you have one.
I don't know.
Okay.